Let's start, I think. Let's get started. Hello. This is lecture 12, and today we will discuss Leuponoff's second method. Okay, so in some sense, it will be the continuation of the preceding lecture. The preceding lecture, we discussed how the stability of a critical point can be studied using the linearization of the autonomous system, right? So if we consider an autonomous system, I will write it as, let it be f capital of xy, and y dot equals g of xy. I will use physical notation for the derivative. So this is an autonomous system, and if we want to study the behavior of the system near critical points, and we are particularly interested in the stability and asymptotic stability of trajectories, because this is the most important question for systems that come from physics, right? And so it is important to be able to analyze stability and asymptotic stability. And on the preceding lecture, we tried to linearize this system. And today we will consider the origin, right? So at the origin, suppose the origin is a critical point and is an isolated critical point, and by linearizing it is possible to determine the stability of the original system. And to do this, we'll look at the eigenvalues of the linearized system, and if so the eigenvalues can be represented as alpha, so they can be real or they can be complex, alpha plus or minus beta I, right, or maybe real. And if the real part is all the real parts of all eigenvalues are greater than 0, then our system is unstable. If all the real parts are negative, then our system is asymptotically stable, and it will remain stable for the original system, non-linearized, right, original system. But if we have at least one positive real part of at least one eigenvalue, then the system will be unstable. But we can't answer the question about the stability of the critical point if it is a center, right? So in the case when all the real parts of the eigenvalues are 0, then we can't answer the question about the stability of the original system. It may be stable, asymptotically stable, or unstable, but linearization can't help to answer this question. So the center is the most important, the most complicated case, maybe, right? Okay. So today we will consider the second method, Leuponoff's second method, or direct method. So this Leuponoff second method is referred to as a direct method because it will help us to answer the question about the stability without knowing the exact solutions of this system. So we need not know the exact solutions of this system. We needn't be able to solve this. But if we are able to construct some function, it is called a Leuponoff's function, which possess several properties, then we will be able to answer to answer the question about the stability or instability. So this is the second method. And so it takes rise from the energy, right? From physics, right? It can be explained physically, and I will try to give an idea of this method using the equations for pendulum. First, undamped pendulum, and then we will take into account the damping force, and we will try to analyze the equations of a pendulum, oscillating pendulum, using so by constructing Leuponoff's function. Okay, and I will give the idea maybe. So this idea will also give idea to Leuponoff, who created this function. Well, so pendulum, oscillating, the equations of a pendulum. Okay. So we start with the undamped pendulum. Undamped pendulum. I recall that the undamped pendulum. So I will draw the figure. Yeah, so it is a mass attached to the weightless rod of length L. So this is mass M, and the other end of this rod is fixed at the origin. This is the origin, and so this mass is free to move in the plane, in our plane, but so this length is fixed, right? So it may oscillate in the plane, in our plane. And our goal is to so last lecture we I wrote the equations that describe the oscillation of this mass, of this pendulum, and we tried to to make ideas about the behavior of this pendulum, so about stability or asymptotic stability of the motion of the pendulum. But our theory studied last lecture can't help to do it exactly, right? So physically, we can expect that this position, this equilibrium position, is stable, and the vertical position is unstable, because physically we know, so we have some experience with motion of this pendulum, right? And so we can expect something, and we can well, have ideas about this motion, but we want to obtain the exact answer about the stability of these positions. And in addition, I want to introduce the idea which give rise to constructing creation of the Leuponoff's function. Well, so I start with the equations. Okay. For the undamped pendulum, the equation of motion was the following. So m times d2 squared theta over dt squared. So theta is this angle. I recall that theta is this angle. Okay. Plus gl times sine theta equals 0. So we don't take into account the damping force because our pendulum is undamped. So that's all. And if we introduce new variables x, so x to be equal to theta and y is x, so dx over dt, then this equation can be rewritten as x 2 primes or 2 dots, it's better, right, plus g over L times sine x equals 0. Or we can rewrite it as a system using these new variables in terms of x and y. This can be rewritten as x dot equals y and y dot equals, it is x 2 dots, and so it is minus g over L times sine x. Okay, these are equations, pendulum equations. Okay, so the underlying idea of constructing of Leuponoff's function is related to the physical principles, two physical principles for conservative systems. So okay, so they are, so the first principle is so a rest position is stable if the potential energy is a local minimum. And it is unstable otherwise. And the second principle, that the total energy is constant during any motion. Let's try to use these two principles in to study the motion of our undamped pendulum. Okay, so first of all, let's start with the potential energy. Do you know how to write down the potential energy? I think Kasia knows. Right, so mgl 1 minus cos x, yes. So this is the work done in lifting this pendulum to this height, so above the lowest position, right? So the work done by them. So gravitational force. So this is the potential energy. Okay. Well, and okay, so our potential energy is greater or equal than 0, right? If x is greater than 0, or so if x is not 0 but near 0, local minimum. So because if x is 2 pi, it is not 0 but So and near between minus 2 pi and 2 pi, then u of xy is greater than 0, and u of 0y is 0. Okay. So this is to verify the first position, right? So the first principle. The potential energy is a local minimum. Then let's discuss the total energy. The total energy. How to check that it is constant during any motion described by these equations. How to check? Sorry?
Add up kinetic energy, potential energy, take partial derivatives.
Take partial derivatives, yes, with respect to this system, yes, without finding the trajectories. We can substitute, so first of all, we must write the energy. Let it be denoted by V. So this is the sum of the potential and kinetic energy, yes. So the potential energy is this, and plus the kinetic energy, 1/2 m L squared, y squared, right? Y is x dot, so y squared. So this is the total energy. Now we want to find the derivative of x. So how to prove that it is constant during any motion? We must consider a trajectory. X of t, suppose it is x of t, y of t. And since this is a trajectory, it must satisfy our system, this one. Sin x. So let's see the G over L. G over L sin x. Well, and we want to find the. We must find the derivative dv over dt along this trajectory. How to do this? We must use the chain rule, right? The chain rule. So we must take the partial derivative, dv over dx, let it be, I will denote it by v prime x, times x dot, plus v prime y times y dot. Okay, this is by the chain rule. It is not interesting for follow. Yes. It is not interesting for you because this is physics, right?
Will this be the test as well? You know physics like that?
So this is just to explain how to construct Leuponoff's Leuponoff's functions.
Do we need to construct the Leuponoff function?
Yeah, so it must be explained what give rise to Leuponoff function. So of course this process. So if we find let's find the derivative of v with respect to t, and we must prove that it is 0. Let's differentiate this with respect to x. It will be mgl sin x. Then x dot can be taken from here times y. Then plus the derivative of v with respect to y. So we must differentiate this part. It will be ml squared y times y dot is minus g over l sin x. Okay, can you check whether it is 0 or not? Is it 0 or not? Yes, yes. Well, so it is magic in some sense that we are able to differentiate this function along the trajectory without knowing exactly, without actually solving the system, without knowing this trajectory, right? We are able to differentiate, to find the derivative of v with respect to, so the rate of change of v with along this trajectory without knowing it. Yes. So this proves the second principle. But now suppose, okay. So first of all, let's discuss them. Let's discuss the stability. Let's discuss the stability of the system. How can it be discussed? So, is it stable or not? Now, well, so it is. Okay, can we answer this question? Is this lower position? So the case when x is 0 and y is 0 is stable or not? Is it stable or not? It can be proved by principle number 1, because the potential energy is local minimum at this point. Yes, so it is stable. And then how see the trajectories? Now we can so imagine that it can be oscillates. It can so the pendulum can oscillate infinitely, right? But if we want to draw trajectories in xy plane, what do they look like? How to how to no, so in xy no, so because so like this, so we can't this process doesn't visualize the value of y. We can't see the value of y. So at this position, y is non-zero. So it's not this. So in xy plane, x is the same as theta. So I think it is clear that it oscillates. But what about y? Up and down, and totally. So ellipse maybe, yes, and the form of trajectories can be taken from this equation. Yes. How to draw? Just a moment. So, well, so since we know that the total energy is constant along the trajectory, yes, so we can try to draw the trajectories when x and y are near. So this point is near the origin. If x and y are near the origin, then 1 minus cos x is approximately x squared half. And then we're trying to visualize the following: 1/2 mgl times x squared plus 1/2 ml squared y squared equals c. Then we can divide. So let's rewrite it in this form: x squared. And if we divide by c, we will get the following: c, so 2c over mg plus y squared 2c over ml squared equals 1. And so we can see the ellipse. Well,
Did you think one L?
L. And so we can see that this is an ellipse, and so the trajectories, the orbits are ellipses, and so we can see that the motion is stable. So using just the energy. Well, now let's consider the damping force. Let's include the damping force to our consideration, and try to. So we will add something to the differential equations, and then after this we will try to find the rate of change of the energy, total energy along the trajectories. Will it be 0 or not? What is your opinion? If we include the damping force to our consideration, not 0, because the system is not conservative, I think. Yes. Well. Huh?
Because the plus infinity will be 0. Yes.
Maybe. Yes.
Maybe.
Yes. Yes, it will be 0. Yes. Now let's add something to these equations. If we include the damping force, we will get the following. So we must add, so I will have a look, we must add C over L, yes, times d theta over dt equals 0. And then this will give us plus C over ml. This is y equals 0, and we must subtract C over ml y. Okay, so one more term for the damping force. Okay. Now let's consider the same total energy and try to find the derivative of this total energy along the trajectories with respect to the system, or with respect to the system. Let's find the derivative. V dot is equal to okay. So that the derivative of this part will be, so I will write this first, and after this I will substitute the result of differentiation. Well, Vx times x dot will give us mgl sine x times y plus ml squared y times y dot is minus g over L sine x minus c ml y. Okay, and the answer will be, so these two terms will be cancelled out. But we are left with this term. It is equal to minus C L y squared. Okay, it is not 0, but it is negative. It is not negative or equal to 0. It is equal to 0 only for y equals 0. And if y is not 0, then it is less than 0. So the potential energy is decreasing along the trajectory. It is decreasing along the trajectory. The total energy is is decreasing along the trajectory. Okay. So we and we expect that it is and v is 0, so v itself is 0. If xy is the origin, yes, so it is clear. So if we look at the formula, at this formula, we can see that near 0, v of xy is positive, and it is equal to 0 only at the origin. And otherwise, it is positive, near 0. Okay, and so it is natural that if so this is a continuous function. Yes, v is a continuous function, and it takes the minimum value at the origin, and it is greater than 0 at other points. And so if we approach the origin, then v dot must be 0, must be negative. Yes, must be negative. So it is positive. In just a moment, I will draw the phase space x and y. And if we start at the point near the origin, so v is 0 here, and v is positive otherwise in some domain, in some neighborhood of this origin, it is positive. And so since v dot is, so the derivative of v is negative along the trajectory, this means that we must approach the origin as t approaches plus infinity. Okay, and so this position is stable, must be stable. Yes, so it is natural, and I think this fact inspired Leuponoff to create his function, and his idea was to consider, so if we consider the general function of this general differential system of this form, maybe this system comes from physics, from some physical experiments, or maybe, so it may not be necessarily it may not necessarily come from physics, but if it is possible to create a function with the similar properties, right? So idea v of x, y with similar properties. So it will play a role of total energy. Well, such that it has some properties. So the first property is v of x, y is greater than or equal to 0, and v of x, y equals 0 if and only if x, y is the origin. And if v dot of x, y is negative, so the same, so along trajectories, then this means the stability of the system. Stability. Yes. So the idea is to be able to construct this this function. Okay, shall we have a break and then? Okay, I will give exact definitions. So no physics from now on, right? So only a description of the Leuponoff function. Okay, first of all, we will need the following definition. So definition number 1, for positive definite, negative definite, positive semi-definite, and negative semi-definite functions. Okay, so the function v of x, y defined in some domain D containing the origin is called positive definite. Let's start with the positive definite. Positive definite if, do you know the definition of the positive definite? So first of all, I will require that v of 0, 0 is 0. It must be 0. And it must be positive otherwise. Then it is positive definite. It is 0 only at the origin, and it is positive otherwise. So negative definite. So likewise, so negative definite. V of 0, 0 is 0, and v of x, y is less than 0 otherwise. Then positive semi-definite. If what? If this inequality is non-strict. Yes, if v of 0, 0 is 0 again, but v of x, y is greater than or equal to 0 otherwise. For any x, y in D, so we may include 0, 0. And negative semi-definite. So if v of 0, v of 0, 0 is 0, and v of x, y is less than or equal to 0, for any x, y, and D. Well, okay, so let's consider an example. Let's consider the function v, which is equal to sine of x squared plus y squared. Okay, is it positive definite, negative definite, or what? So we must describe a domain first, yes, because so v of 0, 0 is 0, of course, yes, but it is x squared plus y squared, is it? Yes, so it D is some domain, and if we describe domain, then we can speak about this function. Yes, let it be. It may be open or closed. So let's consider domain. Example number 1. Let it be x squared plus y squared is less than 1, for example. If this, then what about the function v of x, y? Is it positive definite or not? Positive definite, of course. Yes, because the sign of some positive angle which is less than 1. So this is
Sine of 0 square plus 0 square is 0.
yes, yes. So if so it is 0 only at the origin. Otherwise, it is greater than 0. Otherwise, x squared plus y squared is greater than 0 but less than 1, and so sine is positive. So it is positive definite. And what about the function given by x plus y squared? Is it positive definite? So what about this? So positive definite, negative definite, positive semi-definite. Positive semi-definite, yes. Is it clear? So because it is greater than or equal to 0, v of 0, 0 is 0. But if we take y equals minus x, then v of x and minus x is 0. X is not 0, but v is 0. And so it is not positive definite, but it is positive semi-definite. Well, so we have discussed the definite, so positive definite and negative definite functions. So definition number 2, we must define the derivative of this function with respect to the system. So we must consider the system given the system x dot equals f of xy, y dot equals g of xy, given autonomous differential system of differential equations, and given the function v of xy, we can define the derivative of v with respect to the system by the formula v prime x times f of xy plus v prime y times g of xy is called a derivative of v with respect to the system. To the system. Okay, is it clear? So it must be motivated by the chain rule, right? The chain rule. So if we try to find the derivative along the trajectory, we must take the partial derivative of v with respect to x and multiply by the derivative of x with respect to t. It is x dot, yes, and this is y dot. But if we know the system, we may substitute these functions for the derivatives of x with respect to t and of y with respect to t. So we can compute the derivative of the function with respect to the system without knowing the exact solutions of this system, without knowing the trajectories. We know, so in spite of the fact that sometimes we can't find the exact solutions to this system, we can find the derivative of this function with respect to the system along the trajectories. Well, and now I will state two theorems. I will not prove them. This will be two Leuponoff's theorem. It will be Leuponoff Stability Theorem and Leuponoff Unstability Theorem. So I will use that part of the blackboard. So Leuponoff Stability Theorem. Leuponoff stability theorem. Okay, suppose the autonomous differential system of differential equations. I will rewrite it. Has an isolated critical point. At the origin. Okay, if there exists the function v of xy in some domain in D, and this function must be of class C1, so it must be differential together with its partial derivatives. There exists a function such that requirement number 1, v of xy must be positive definite, and v of xy with dot, so the derivative of v with respect to the system. So in formulating, in stating this theorem, I take in my mind the total energy. So it's the way to memorize this, right? So it must be positive definite because the energy is positive definite, right? For the system of oscillating pendulum, yes, the energy is positive definite, and the derivative must be. So for stability or for asymptotic stability, it must be so let's look. I removed them. What is the negative? It must be negative. Yes. So to approach zero asymptotically, it must be negative definite, and then it will decrease. Then the energy will decrease along the trajectory, and so it must approach the origin. Yes, so this is the logic. Well, is it true? So if it is positive, if it is positive here, and if the energy decreases along the trajectory, then it will approach the origin where the energy is zero. Is minimum, yes? So it must, so it's negative definite. Okay, then it is, so this critical point is asymptotically stable. Asymptotically stable. So if instead of this, so if v of xy is positive definite and v dot is negative semi-definite, then it is just stable. the origin is stable. Like in the situation for undamped pendulum, yes, for the undamped pendulum, so the energy is positive definite, but V dot is equal to 0, so it is negative semi-definite. Then it is stable, just stable. We can't state that it is asymptotically stable. It is stable. Well, and Leuponoff Unstability Theorem. So I will use, so I want to, remove this. I think I will use this part of the blackboard, yes, on the green board, to state the unstability Leuponoff theorem. Okay, so the beginning is the same. Suppose the autonomous system has an isolated critical point at 0, 0, and if there exists the function, so S, so there exists the function in D of class C1 such that, so the beginning is the same. I don't want to rewrite it, right? So V of xy is of class C1, and okay, so I will not require that it is positive or negative definite itself, but it must be positive at some point. So there exists point at which it is okay. Just a moment. V of xy must be. There exists a point x0, y0 in D such that V of x0, y0 is greater than 0, is positive at one point. Okay, and V dot of xy is positive definite. Then the origin is unstable. The origin is unstable. Okay, I will omit the proof, but we will consider examples. And first of all, now we will treat the equations for oscillating pendulum. We will start with the oscillating pendulum, and after this we will consider other examples. We will try to construct different functions. We will try. So these are two theorems. And so the difficulty in application of these theorems is how to construct this function. Okay, so the answer is, if our system comes from physics, then the recommendation is to try energy, right? To try to take the energy as the function v of xy, to be the function xy, v of xy. But if this system is not related to physics, then you should use trial and effort method, yes, to find the.
Can we find two different functions
So to have both. So is it possible to have two functions? V1, so V1 for the stability theorem and V2 for instability. Of course not, because this will be the contradiction. So if we prove this theorem, then for the system it is impossible to be stable and unstable simultaneously. Yes. Okay. Proof. So no, I have decided not to prove, but let's consider examples. Well, so first example. I told about this example, undamped pendulum. And so the energy is this function, V of xy, which is equal to mgl 1 minus cos x plus 1/2 ml squared y squared is this function. Is it positive definite? Let's check. Is this function positive definite or not? So 1 minus cos x is non-negative, of course, and it is equal to 2 sine squared x half. It is non-negative. Yes. We can see that v of 0, 0 is 0. And if x or y is different from 0, then this component or this must be non-zero. And so it is positive otherwise. Not non-negative, but it must be positive, because this is the sum of two non-negative terms. If x is non-zero but close to 0, then this part is negative, is positive. Yes, and if x is 0 but y is non-zero, then this part is positive. And so this function is positive definite. And what about this second requirement? So the second requirement, v dot must be, v dot, yes, v dot. What about v dot? If we have the undamped pendulum, then v dot is equal to 0. Or maybe so I think in physics usually so they usually use dot, and so I use this notation, but this is the same as prime. Oh. Yes. The derivative with respect to time. So sometimes it's better to use dot. Well, so v dot is 0. Then is it negative definite or negative semi-definite? What is it? Which property it satisfies? Yeah, negative semi-definite. Negative semi-definite. Yes, negative semi-definite. But not negative definite. It is definite negative semi-definite. Negative semi-definite. And so this position, the origin is only stable position, not asymptotically stable, but stable. For a damped pendulum, it is only stable, but not asymptotically stable. Okay, but it is not. So let's look at the Leuponoff Unstability Theorem. So V is not positive definite, but it must be positive at just one point. If there is a point at which it is positive, yes, for this function, the first requirement is satisfied. Yes, but let's check, is it positive definite or not? Positive definite. Of course not. V is not positive definite. Yes, because V dot is 0, so it is not positive definite. So the hypothesis of this theorem is not satisfied. So V dot is a constant. No, V dot is zero. V dot is zero. It is negative semi-definite, but not positive definite. It is not.
What about positive semi-definite?
It is positive semi-definite. Yes, it is also positive semi-definite, but the hypothesis of this theorem is that it must be positive definite, not semi-definite, but it must be positive definite. So we can't state that it is unstable, but we can state that it is just stable, not asymptotically stable, but stable. It is stable. So this position is stable for undamped pendulum. But what about damping force? Damping pendulum. Yes. So if we consider the same energy, yes, the same function for damping force, for the pendulum with damping force, so it satisfies the motion of the pendulum with damping force, satisfy these equations. And if we try to find, so it will be example number 2. Example number 2. So pendulum with damping force. Then we have, it is described by this system of differential equations. And we take the same function to be the energy, the same function, and try to find the derivative of V with respect to this system. And we have already do this, and I will rewrite the answer. The answer was, so just differentiate this, it will be ml times y, and times minus, it comes from here, minus c over ml y. Yes, it was minus cy squared. Yes, as I remember. Am I right? I think it's this. Minus cl or l. L squared. Cl minus cl. Cly squared. It is negative semi-definite, not negative definite. It is negative semi-definite. Can we claim that so this critical point, the origin is asymptotically stable or not? Having this result. So V is positive definite as before. It's okay. So the first requirement is satisfied, and the second requirement is it is negative semi-definite. Yes, it is not unstable. It is stable. But what about asymptotical stability?
It becomes zero.
Yes, it is not. It is negative semi-definite. And no conclusion can be drawn from this function. Yes, about asymptotic stability. So it follows that it is stable, but we can't make any conclusion about asymptotic stability from this function. Yes. So we should take another function. Let's take another function. Let's change the function. Find find some other function which is positive definite. Asymptotic stability. so the step, let's consider critical point, right? It is 0 of these two functions. And the asymptotic stability means, so first, stability means that for any epsilon, there exists delta such that if we start within the circle of radius delta, then we will remain inside this the circle of radius epsilon, right? So this is simply stability, just stability. Asymptotic stability means that we must approach the origin, this critical point, as t approaches 0. So the limit of yes, so as t approaches positive infinity, the limit of this must be 0, 0. It must approach 0. It must approach 0 as t approaches positive infinity. This is the so in addition to be stable, right? And this means asymptotic stability. Asymptotic stability. So we should change the function. We should change the function. Well, so just a moment. I will write them. So if these coefficients are ones, then I can write the function, but I will try to change it. Just a moment. I will have a look. What shall we do with it? It's better. I think it would be better that I will write the function for so let's make a change of variables to make these coefficients to be ones, right? Right. It will be better. Maybe it's better to explain. Let's consider this system minus sine x minus y, and then having this system, let's try the function v of x y, which is equal to so as before we start with so all the constants will be 0, and so we start with so the kinetic energy will be 1/2 y squared, then plus x squared, and then plus 1/2 x plus y squared. So this function will work for the system. Yes. So if we equate all the constants to be 0, to be 1, yes, then this function will work for this system. Let's try to find. Okay, let's discuss this function. It is, of course, positive definite. Yes. So I will take this function from the book. So it's not my creation. It is sometimes it is difficult to construct this function. But yes, how to? So you should try different functions, and we will try to solve some problems during the seminar, and I will give you hints for the homework, how to, so what is the form of the function. So usually near the origin, positive definite functions will have the form of a times x squared plus b times y squared, where a and b are both positive, some positive values, right? And usually we can look for the function in this form, and this will be the hint, and we will try these functions. We will not go into, so we will not study advanced problems when, so it's some skill to construct this function. Well, now let's consider this function. I took it from the book, and so let's just check that it satisfies the Leuponoff stability theorem. It is positive definite, of course. It is easy to check this. V of 0, 0 is 0, and it is positive. Now let's take the derivative of this function with respect to this system. So let's differentiate this. It will be y times y dot. Y dot is minus sine x minus y plus then 2x times x dot. X dot is y. Then plus, let's differentiate this. It will be x plus y times x dot plus y dot. I will write it first. And then substitute. So this will be minus y sine x minus y squared plus 2xy plus x plus y. X dot is y, and y dot is so minus sine x minus y. These two terms are cancelled out. Then we will have the following: minus y sine x next minus x sine x minus y sine x. Okay, now let's get similar terms. Similar terms are this, yes, this, and minus, just they. So minus 2y sine x next is it true? I think it, okay, yes. Plus and in these terms, so it will be minus y squared plus 2xy minus x sine x. Okay, let's try to discuss this. Why is it so? It must be negative definite. But why? Let's try to rewrite it in some form which will prove us that it is negative definite. Just a moment. It must be so 2y x minus in this form, I think. So not this. So x minus sine x. Just a moment. Just I will use the approximation of sine. I think it's better to use the approximation of sine. Yes. I will substitute something. So let's consider sine to be so it is x minus using the Lagrange's formula, it is the third so f sine triple prime, yes, of c divided by 6 times x cubed, where this is the derivative of sine. Yes, the third derivative of sine. The first derivative is cos. The second is so minus sine minus cos. Yes, it is plus cos. Using the Lagrange's formula, right? It is plus cos 6 times x cubed. let's substitute this for sine x, and what shall we obtain? Minus 2y x. Yes. Next, so psi is
What the function v, the domain is real number.
yes, real numbers, but so we need the domain near real numbers, yes, but it is locally stable, yes, and so we can consider the domain just near the origin, inside the circle of very small radius, right? So to use this approximation, well, minus 2yx minus 1/3 cos psi times yx squared minus y squared plus 2xy minus, so this is minus x squared minus 1/6 cos psi x to 4, and it is equal to, so these two terms are cancelled out, and so we have minus x squared plus y squared, and plus terms that are sufficiently small with respect to the radius, right? 1/3 cos psi, it is so it doesn't exceed 1, right? X squared y minus 1/6 cos psi x to 4. So these two terms are small in comparison with x squared plus y squared. They are terms of so this approach 0 much more faster than x squared plus y squared. So near the origin, these terms are so negligibly small, and so we can state that v is negative definite because of this term minus x squared plus y squared, right? So this part approaches 0 faster than the radius.
So my question is about this part, dx y 1/2 y squared plus s squared plus this part. So what from this part when we go to the v dot, this in differentiation, right?
Okay, so differentiate this, yes. So the derivative of okay, this is y dot. Yes, so we differentiate this, so y times y dot, but y dot is minus sine minus y due to this system.
But
Yes.
why is it y multiplied by y dot?
Y what?
А почему это y
Times y dot. Because when we differentiate this with respect to the system, so then I will try to explain. So we want to find dv over dt. By the chain rule, it is the partial derivative with respect to x times so dx over dt plus dv over dy times dy over dt. And so if v is 1/2 y squared, then dv over dt is equal to, so this is 0, but dv over dy will be, so if we differentiate with respect to y, we will get y. And next we must multiply by dy over dt, so y dot. So this is just chain rule. And after this, we must use the system to substitute y dot, which is equal to minus sine minus minus y. Okay, just differentiate x squared with respect to x. This will give us 2x multiplied by x dot. This is x dot. Then substitute y.
It's confusing, but
Yes. So I do it a little bit fast, yes, so
Yeah, but I
should be step by step. So now it's a break, and we may continue after the break, yes. So I have finished with this example, and after this we will try to solve something